Okay, can you guys see the screen all right?
Yeah.
Okay, great. So I'm going to be presenting on visual, textual, attentive, semantic consistency for medical report generation. Um, Motivation behind this technique, and this is again for medical report generation. Um, Medical staff are overwhelmed by caseloads and feature-rich data. The manual examination of X-ray images require radiologists who are expensive and can often make errors. Um, an article from Insights into Imaging from the Journal of, which is the Journal of the European Society of Radiology, found that errors and discrepancies in radiology practice are uncomfortably common, with an estimated day-to-day rate of 3 to 5% of studies reported, and much higher rates reported in many targeted studies. So what if diagnoses and documentation from X-rays could be automated in an intuitive way? The methodology that the authors proposed was to process multiple modalities, the chest X-ray image itself, as well as a clinical description of the patient. And they used both convolutional neural networks and attention mechanisms to find and correlate features between the images and the text descriptions. They then generated confidences for key findings and a detailed report that you can see in the far right green there. So the methodology that they used consists of three main parts. First was encoding for all of those different features. They then proposed this multi-modality semantic attentive learning technique, and then progressive report decoding. So I'll touch on each of those individually, but if you look at the top left, in blue is where they start encoding for features from imagery. In the bottom gray portion is where they start encoding for the text-based features. On the top right corner is how they compare it to their ground truth, what the actual report came back as from the clinician that they used to train the model with. And then in the bottom in green is how they decoded full sentences for a medical report. So starting with that visual feature decoding, fairly straightforward from a lot of techniques that we've seen before. The visual features were encoded using the backbone of a DenseNet 201 model. What they call regional feature is extracted from the last dense block, and that's just the activation surface, that 14 by 14 by 2048 block right there. It's just the activations from that last dense block. They then applied a self-attention model in order to compute more weights to be used later in their, both for their multimodal self-attention, semantic attention module, and then also to compare that with features to be compared in the global features vector there with features that they found in the actual report itself. So that'll also be compared later. Encoding for those clinical text features. In clinical scenarios, radiologists often use a few simple factors when looking at an X-ray image. In this case, they used the reason why the patient had been admitted for, say, chest pain in this case, the age of the patient, and then the biological sex of the patient. So they used a combination of an already standard encoding practice for medical terminology, which was BioWordVec for the reason embedding. And then they combined that with a simple embedding for the age vector and the sex vector, which was Sex was easy binary, 0, 1. Age was split out into 20 values that represented 5-year increments from 0 to 5 years to 95 to 100 years old. So the output after concatenating all three of those was it was cast into a 256 dimensional feature vector. For the report encoding, they used a similar, it was actually published by the same people who wrote the BioWordVec encoding. They used the standard sentence vector encoding, which used 700 features. So each sentence was encoded into a 700 feature vector to use for comparing to the rest of, say, the output of the decoder. They also used disease labels and description pattern labels. So that was based on, again, an already established automated rule-based labeler. In this case, if any description pattern label was positive, that means that the word appeared in the report, and if it was negative, it didn't appear in the report. And they used just a binary loss to find out, to learn if those words were encoded in the final report or not. The labels are also predicted for some top number of probabilities, and those are selected and correspond to different word level embeddings used for that were extracted from the BioSentVec as well. So down to the meat of the technique was their multimodality semantic attention mechanism. So the authors thought, in order to obtain a concise context that focused on a single topic at each time, they would use 3 semantic attention mechanisms that were computed with respect to, first, the image features in the top half here. Secondly, with respect to the clinical features and the text description seen at the bottom in gray. And then finally, with respect to the top K predicted labels from the common medical descriptions. So just to define again what the self-attention versus semantic attention is. Self-attention computes attention with respect to the inputs themselves. In this case, semantic attention is implemented here as a soft attention mechanism that provides some coherent relationship between the inputs and when they're actually needed. Again, the attentions are computed with respect to both the hidden decoder states, H, in the far right side of the equations, and it's done 3 times with respect to each of the different inputs being processed. So these attentions know when they're being used, and also from which modality is being explored. For finishing the computation of the attention, for context and labels, those semantic attentions were directly computed using their input features. So you can see equations 5 and 6 there. Use what we had previously seen multiplied by those vectors themselves. But for the imagery, they wanted to include an extra term that included both the semantic attention and just pure self-attention with the features computed from the image encoder. So they added another term in equation 4, and then they just weighted both of those terms by 2 learnable parameters gamma for the semantic weight, and then gamma for the self-attention weight. And then all of these three attention weights were then passed to the decoder to give it context in relation to all of these different modalities that they were analyzing. Again, just to stress that this context depends on each time step in the decoder. All right, the h of t minus 1. So for each previous time step, the hidden weights from the decoder are passed to the attention so that it can understand its context within second to come back in.
Yeah, sorry.
Okay.
I think there's a unstable connection here. Yeah, I'm back. Please go ahead.
No worries. So the sentence decoder just predicts sentence level embeddings. This isn't actually predicting the words that would be used in the report. At each topic, for each time step, the LSTM takes the input that we saw concatenated from all of the different inputs, the CTX vector and the hidden states, to output two different things. One is the predicted sentence embedding, and then a continue or stop vector. So it tells you, I predict this vector for what is the context that should be contained within this sentence, and then also should I write another sentence or should I stop here? And then moving over to the word decoder, this takes in the sentence embedding and translates that topic into individual words from the start token to the stop token. So this part is what actually decodes each sentence and says, start, what is the actual description of that topic and what word should I use in series. And this was implemented using just a single layer LSTM. There were also 4 unique loss functions used in this paper. So it was computed from multiple components like the continue stop signal, the sentence embeddings from the ground truth, which were just called the sentence loss, an image sentence matching loss, the ISM loss, and then from the description accuracy, there was another loss computed there as well. And then the output of each step was connected to the next word token, and a cross entropy loss was computed there as well. So the results of this were that the full approach, using all of the features, all of the attention mechanisms that they introduced, that was compared to other versions of the same approach without certain components. For example, you'll see descriptions of hours without, say, DPL there, which was description pattern labels. In general, the full approach does a better job of retaining all information over all other approaches. And below is just one example of the text description of the text from one of the generated reports for 4 different approaches here. In hours is the report generated using all of the techniques mentioned. In green is highlighted the correct labels, in red is highlighted things that were wrong in that full generated report. And some of the metrics that they used to evaluate this technique were common image captioning metrics like BLEU, Rogue Meteor. Those all focus on word level fluency and recall. In this paper, the authors also proposed their own metric, which was normalized key term distance, which judged specifically whether or not the generated sentences contained all of the observed diseases and their detailed descriptive information. This was just based on the Hamming distance between all predictions and the ground truth, and was normalized by the number of labels within the ground truth. Onto the results. Although some of the experiments without certain components beat the full methodology, for some cases, for some metrics, I'd say, it's often by a small margin, and the full approach consistently beats all other baselines across actually all metrics. So if you look down at the bottom, when you see hours, the very bottom line in hours, for all 7 or 8 metrics used to evaluate the model, the full approach actually beats the best reported baseline, which is compared above in blue. In red, you'll see that without using the clinical description features, the CF, hours without CF, it does beat the full solution twice, but overall it's the full solution outperforms pretty much everything else. And this was using the MIMIC chest X-ray data set. For another X-ray data set, we see similar results here. In this one, the even more metrics are topped by the full solution. And again, each sample of the full algorithm beats every best instance of every baseline compared. So some of the strengths of this method were that previous methods focused on readable reports, which, while this approach sought to accurately detect and describe findings that matched with the query X-ray. Visual features, predicting key finding embeddings, as well as incorporating those clinical features was definitely interesting and helped them get a better score. Their progressive decoding scheme also showed that the report was semantically consistent and that each line produced in the report would contain all of the necessary features to classify what they were trying to describe and localize it. And then extensive experiments on the public data sets showed that their model achieved consistent improvements over the state-of-the-art baselines. Some of the weaknesses that I noticed were that it was an extremely complicated architecture and computationally expensive. The approach may not scale well to much larger problem sets with larger dictionaries or word embeddings. And some interactions within layers in the paper were not well explained and definitely required a lot of digging, such as how they were mapping from their self-attention to the global features. And they also said that they retrained one of the encodings using their data set, the MIMIC data set, in order to make sure that all of the words were represented. So there may be some reproducibility issues using the standard encoding. path forward, the authors came very, and some critiques, I thought that the authors came very close to a transformer model without directly adopting it, even though it was published in 2021, with few references to those types of architectures outside of the original attention papers. And for a model that uses, CNNs and attention, I was kind of surprised that something like Clipper, Perceiver, GPT transformer models weren't evaluated or even compared to. One thing to note there is that this medical data is typically much sparser than what those transformer models are trained on. So that may be one reason why this approach wasn't compared. And the ratings, I give it a 3. The authors did do a really good job of comparing their results to state of the art, and they showed the effectiveness of each novel contribution when used together. However, the architecture was extremely complicated and some fine-grained details on the implementation were left out of the paper. I thought that including an appendix with notes on implementations and trade studies would definitely help to improve the readability. And that's it. Are there any questions?
Okay, all right. Thank you, Joe, for the presentation. So I think the student can starting to ask questions.
What paper or what date did this paper come out? Because it seems pretty similar to one of the weekly papers that we did review, which that one was a transformer. So I was just wondering, like, what was the order of?
Yeah, I think I have it pulled up. I know it was 2021. I have to find the date, but yeah, I don't see it readily in here. I just know it was published in
It's okay.
2021.
Yeah, it was just because you were talking about how like the future work and stuff, like they should just make it a transformer, which I think this is exactly what one of the weekly papers that we read did.
Let's see, published. It's published in the 2021 copy
Yeah.
of the ICCV, but oh, it looks like it was actually October. So yeah, it's pretty recent. So yeah, that's what I had thought too. It's just it seems like the decoding portion in particular was extremely complicated with multiple different ways of decoding both the topic and then the actual words using different LSTMs. So it seemed like a highly concocted solution that I think could be simplified a little bit.
Yeah, I also feel like this is kind of over-engineered pipeline. You have all these different embeddings, encodings, different architectures. It's really difficult to pinpoint what is the novel contribution. Although they have good performance, but if I look the table you presented, some of the approach is just, I think the latest is like 2019 they compare with.
Right.
So what about 2020 and 2021, right? So there's 2 years missing. Like there's no, why just report, I think the comparison method like 2015, 16, latest is like 2018 or 2019. So
Okay.
just curious, why they compare those methods. Are they, right? So this table here, how these methods, are these representative approaches? Is there any other latest method are missing from the comparison? And you're right. So a lot of other the method like the GPT, right? GPT-3. So they were also able to generate the text based on the image. So I think that would be a very interesting or maybe very straightforward baseline to compare with. And that one is pretty simple, right? So here, their overall method is quite complicated with different modules and different components in there. So I have a hard time to understand like what exactly going on with these different embeddings and how they contribute to the final. Although they have this kind of ablation, right, removing like one of the component, but it's still not really clear, right? How much or how really important is the like one of their modules in the method.
Yeah, I definitely agree. It's seems because it's especially since there are a lot of newer papers that kind of readily dissect different inputs from different sources in a much simpler way. It seems like they could adopt one of those pretty easily and get rid of I think the decoder and this kind of contrived attention mechanism, as well as the CNN, just all of that together is a lot to, it's just a lot of extra additions that could be replaced with probably a single network.
Yeah. But I do think this problem is interesting, and definitely there's a lot of work right now using multi-modalities, like using visual data as well as like text or maybe other modalities. So yeah, I think this problem is interesting, but it's just the method. I'm not quite fully understand like what is the major contribution of the approach. Okay. Any other questions?
No, just a comment also on the same, on the topic of, the model being like overly complicated is, from another angle, especially like in the medical field, it's even more, the more complicated the model, it's even more black boxy, for lack of a better term.
Yeah.
Or it's not as interpretable. So, and I think so that's in my opinion, a pretty big weakness, especially in medical. I think the physicians, I work with physicians sometimes, and they're definitely like, we have to like understand and stuff why it's telling us something.
Yeah, that's absolutely right. So yeah, like more complicated model, it's really difficult to interpret the decision, right? Why, how this model is make such decision, and what is the causal reasoning behind it. So definitely we want to have some simpler model, right? So it's easy to diagnosis or make some of interpretations of the model decision. So I think in terms of practical application, very complicated method wouldn't be able to, be adopted by the practitioners. Yeah. So yeah, that's a very good point. Yeah, and do they do any analysis or comparisons in terms of like a computation complexity aspect of the approach?
No, but I do know that it's trained in multiple stages. It's, yeah, I think it's fairly non-standard techniques that they're using, because they built their own attention mechanisms and use multiple LSTMs. So I don't think this would be a standard architecture that you could readily train yourself.
Yeah, that again creates some barriers for readily adaptation, right? So if there's multiple stage, very difficult to train, and a lot of parameters to tune, that's going to be a problem. So most likely, this system will be used by radiologists. They don't have any maybe technical training from computer science, right? So how do you expect them to train or maybe use the system is questionable. If it's too complicated, it's easy to not easy to use.
So from the from the semantic attention in the from the image features, you can get some overlay, like what's in the center block here. See if I have a better picture. From the semantic attention, you can see where some of the class decisions are coming from, but because it's also correlated to the clinical features and the other embedding of the labels, that can be hard to understand why it's choosing those specific topics as well. So that's it's still difficult there.
Yeah. Okay. Okay. Any other comments, thoughts, or maybe having some ideas?
Yeah, I just kind of have like a general question. If the authors mentioned, like, did they talk about why they did so much? Like what you said, they have very complicated model. Looks like they combined certain, like a bunch of models. So is there a reason they did this? Like, did they think it would probably provide more robust results?
Honestly, I didn't really see that. I mean, they referenced a lot of other image captioning techniques. They wanted to focus on the semantic consistency of the output. And I think that's why it was so contrived, because they wanted to break it down by topic level first. And then that's kind of the structure of the decoder, right? Is doing the sentence prediction or the topic prediction in order first, right? Which is the most important, related to specific keywords from the word encoding up at the top. It's just like a lot of different stages to try and achieve that semantic consistency. Like that's what they were going for.
But it's also like kind of impressive, like how they're able to do all that. I'm just like kind of curious, like as to like if there would be sort of like a practical application to this, maybe towards like maybe multitasking sort of applications.
I mean, then the interesting thing I think is that is from the sentence decoding, because that's really how they're taking like multiple modalities and they're saying this is the most important thing in the data, and then the next thing is what you pull out in the next topic. That's pretty interesting. Other than that, it's like that could also just be from a transformer that sees all inputs at once and you compute your attention and understand it that way. But it's kind of interesting that they pulled out that topic level feature vector first, right? And then decoded that itself into different words. So
that's pretty cool. Yeah, that's all for me.
Okay. Great. Any other comments? Okay. All right. So if not, thank you, Joe, again for the presentation. So I think that's all for today. So we still have time left. So I want to see if you guys have any questions related to the assignment or your final project.
Yeah, Professor.
Yeah.
So taught about the assignment. So I've kind of like tried to run one of the links you provided, the trans BTS. And I'm trying to see if like it can, how I can get it to like compile so I can make sense of it, you know? So I encountered this like kind of weird error. It says like something about rank. Here, let me find it. Yeah, so
Yeah, so I think if you want, you can share the screen so like everyone can see it. So,
Yeah.
you know, this is a common issue. Maybe we can have a discussion.
Yeah, sure. I was just trying to find it. I found it. Let me share the screen. Okay. You guys can see?
Not yet. Okay.
Oh, okay.
Yeah.
Yeah, so I'm trying to run this and then I get this weird, I've never seen this like torch distributed. Like rank expected but not set. Is this like because
Oh, okay. Yeah, this is like a multi-GPU thing. If you're using multi-GPU training, so maybe you have
so
to.
then maybe could I compile this on the Newton server like and see
Yeah,
like
I think
what
you can figure out like some flag. Maybe you can just using a single GPU.
Mhm.
Are you using like a Newton cluster or using your own like a desktop or a laptop?
I think right now I'm just trying to figure out like how this works. I think like if I try to use Newton, I'm going to use like one of the clusters because I think that's how you use like the GPUs available, right?
Yeah, so I think, but again, you have to specify. Maybe just go where the source of the error and see if you have to maybe um, kind of comment like or specify like how many GPUs are you want to do some distributed training.
Hmm. Okay. Yeah, I'll just see if I can figure that out. In the meantime, I guess like anyone else could ask questions. I don't want to just waste time, you know.
Yeah.
Right.
Okay.
I have a project question.
Yes.
So is it okay if we, at this point in the semester, I guess, slightly change like the proposal that we made? Because for instance, I proposed for my project using a transformer for something. But after like going through a lot of the papers in this course and advanced computer vision, I thought it'd be a lot cooler for me to try like a contrastive learning thing.
Yeah.
It's the PIL project, by the way, from the recommendations. Can
Yeah.
I do that if I'm comfortable with it?
Yeah, so that's totally fine. I mentioned this in the first class. Yeah, in the beginning, you are just writing the proposals. During the course of doing the project, you want to change something, that's totally fine. But not like a complete, like a new topic, maybe not a good idea, because unless you have a good reason or you have everything well prepared, maybe you can change that. But you know, small modifications or change, that's totally fine. Okay.
All right. Yep. Thank you.
Yeah.
So I had a quick question.
Yeah.
So I'm trying to get it to work 3D, but I was having a bit of trouble because I've never really used a transformer model. So I was gonna do 2D as sort of a backup, and especially before the deadline was changed. So I'm still trying to do 3D now, but I was thinking about 2D, and I would I have to split up the scan into 4 different images and then process like all like the layers, because I feel like that would be a lot of images, like almost too many.
No, I think are you talking about the second assignment, right?
Yeah, sorry.
Yeah, so the way you can process the data is, so it's those 4 modalities, right? You can consider them as 4 different channels, right? So for the RGB image, we have those 3 channels, right? But for each of the MI slice, instead of like 3 channels RGB, now you have like 4 channels corresponding to T1, T2, flare, and another one, right? So you consider them like a 4 channel image, right? For each of the slice. So for the 3D convolutional kernel is you basically have to take multiple slices. Again, each slice will have those 4 modalities. Unless you don't want to using all the modalities, but it's a good practice to using all the modalities because they present different informations to help you to segment those different tumors. Okay, so ideally we want to using all those 4 modalities. You know, you can treat them as separate different channels, and each slice will be like a 4-channel image, and each slice will corresponding to a segmentation mask. Okay, so if you want to do 2D CNN, then you'll just process each slice individually, right? Rather 3D CNN, you will take multiple slices at a time, and those convolutional kernels will operate on multiple slices to extract those like a spatial and slice dimensional feature. For the 2D case, you will just look at one slide at a time, right? You are not looking at the neighboring slides to get some neighboring information. So yeah, that's the bottom line is that if you're doing 2D approach, then basically it's just like a normal RGB segmentation, right? It's just those 4 modalities will consider like 4 channels. Okay, each slice will corresponding to a segmentation mask. Okay.
Yeah. Okay. That actually makes perfect sense. I just I think about it like that at first.
Yeah.
Like,
but again, I think you have to consider the computing resource you have. If you feel like 3D is very difficult to fit the GPU, maybe try 2D as a backup and using the 2D unit to process.
yeah, that's what I'm doing. I'm trying to use Newton for 3D, but if I can't get it, I'll be.
Yeah. Okay. All right. Yeah, the TransVTS is just like example code because has these pre-processing and evaluation. So that's a very good example for you to get it started, but you don't have to follow exactly. Yeah, you can just switch the backbone from the unit. But if you're doing 2D, then it's gonna be, the pre-processing is still the same. Like you can load the data, pre-process the data, but it's just the training of the data set is going to be different because you are using the 2D approach. For the TransVTS, it's a 3D approach. Yeah, I'm sure you can find a lot of examples like using 2D unit for medical segmentation. Yeah, just if you understand the problem now, right, like I mentioned, each slice has a corresponding segmentation mask. So there's a pretty much the same like you are doing RGB segmentation. Okay, so yeah, I think since we canceled the third assignment, so we have a lot of flexibility in terms of the deadline. So I guess it will be good for you guys to really understand the problem, actually able to train the network for this segmentation task. I don't want you guys to rush. If I receive enough requests, by the end of this month, right? The new deadline is March 20, the last day of March. But if you guys still, have difficulties to finish the project, I can maybe extend another week, so you can spend more time to actually understand the problem, and complete this assignment successfully, because segmentation is a very important task in medical image analysis. So it's like a fundamental task. A lot of diagnosis depending on the segmentation. So I really want you guys able to understand this, get a hands-on experience on the segmentation task. And maybe this will also help for your project. I know some of you also proposed the final project as segmentation task. So it's really help you if you're able to complete this assignment successfully. Okay. Okay, great. Any other questions or anything you guys want to discuss?
Seeing as this was the last paper presentation going forward for these lecture times, what is the plan for during these lecture times?
So how many presentation we left? We still have a couple.
Oh, we still have more. Okay, never
Yeah,
mind. I
yeah.
thought because there was only one today that was the last person.
No,
Since it was
no, it's just
oh, it's just nobody else picked today. Okay, I see. Never mind.
yeah, it's just one student. He withdrew from the class. He told me last week he withdrew from the class due to some other commitment. He couldn't finish. I think probably we have a lot of assignment and tasks to do, so maybe kind of overwhelmed. Yeah, we do have a couple of more presentations, but after the presentation, we'll go for the final project presentation, which I will also, send out announcement, ask you guys to schedule the time. So that's pretty much gonna be the rest of the schedule of the class. So I think the remaining time for you guys will just focus on, completing the final project. And we still have like a 1 or 2 paper reviews. So yeah, so other than that, I think, yeah, there's not much there. Yeah, but if you guys need, have any other things you are interested, you wanna me to, talk about, yeah, you can also let me know. Maybe I can squeeze some time to have an extra lecture to give you some of those topics. Okay.
Okay, great. Thank you.
Okay. All right. See if you have any more questions. Okay, great. So yeah, let me know if you guys have any questions. And yeah, we have office hours on every Tuesday. So I think if you have any questions, you can also ask during the office hours or just send me email. Okay. All right. Thank you guys. We're gonna end here. Have a nice weekend and I'll talk to you next week.